Hello and welcome to the 11th lecture of the machining science course. So, let me remind you, in our earlier session we were discussing the Zorev's model of friction, and what we said is that here is the distribution of the normal shear stress along the chip tool contact length, which is LF, and this is how the distribution looks like of the shear stress. Now, here the shear stress remains constant in the sticking zone, as we said, because the normal pressure is very high, and when the normal pressure decreases in the sliding zone, the mu remains constant. So, therefore, the towards the point where the chip loses contact with the tool, this is decreasing, that is the shear stress. Now, if we integrate this curve from 0, x value is 0 at this point and x value is LF at this point. So, in that case we can actually find out the normal force, that is what we did here, all right. And then we have integrated this area under the shear stress and we found out the shear force, that is what we got. Then we have simplified the formula of the F, and initially by integrating we got this, we have simplified by substituting equation 3 in this equation, and we got this. So, then the F by N, we got the tan of the friction angle, and therefore, the friction angle can be found out as the arc tan of this. Next, we said that the mean normal stress on the tool face is given by this. We found out the mean normal stress, and that from there we can find out the sigma f max, which is 1 plus y into sigma f average. So, therefore, finally, we get that the friction angle is this, and it was said that this factor remains sufficiently constant in practice, and therefore, this can be assumed to be equal to arc tan of some constant, which is this, all right, divided by sigma f average. So, this equation shows that the mean angle of friction is mainly dependent on the mean normal stress on the tool, sigma f average. This explains the following fact: as working normal rake increases, working normal rake is alpha n, working normal rake, that is a normal rake. The component of the resultant tool force normal to the tool face will decrease. If you remember, we said that as the cutting force in the diagram of the cutting force and the alpha, all right, we said that this has this nature. So, as the alpha is decreasing, Fc is increasing and vice versa. So, therefore, this is the same thing we are saying here: as working normal rake increases towards this, the component of the resultant tool force normal to the tool face will decrease, all right, because of this, as we have explained in this curve, and therefore, the mean normal stress will decrease, and if it is decreasing, then the friction angle will increase. So, this is the conclusion that can be made from the Zorev's model, and this is very important when the working normal rake variation is considered and how to select the working normal rake. Okay. Our next topic will be the practical machining operations, and here in this slide you can see there are various machining operations, practical machining operations like turning, milling, drilling, shaping, planing, broaching, sawing, these are shown here. Now, in turning, for example, you can get the cylindrical surface or groove, or the threaded part or the threaded surface. In milling, normally the flat surfaces are obtained, or the grooves or the contours, very complicated contours, if for example, it is the CNC milling. In drilling, normally the holes are drilled, either it is a blind hole or it is a through hole. In case of sawing, it is a parting off, that is we are parting off normally the two parts. In broaching, these are the internal slots or external slots. This can be machined at a very high accuracy. And the shaping and planing, as you know that in case of shaping, the tool moves to and fro, reciprocates, and the workpiece is given the feed movement perpendicular to the movement of the tool. And in case of planing, it is the other way around, that is the workpiece moves and the tool is given feed perpendicular to the movement of the workpiece. So, shaping is used when the workpiece is smaller, and the planing is used when the workpiece is very large. So, therefore, depending on that, in case of shaping we have the quick return mechanism, because when the tool is moving forward, it actually cuts, removes the material, and since it does not remove any material while going back, so going back is normally at a higher speed than the forward stroke or the forward movement. All right. Now, in case of planing, the same thing happens. There is a quick return mechanism, but that quick return mechanism is different than the shaping, as many of you might be knowing that there in case of planing, there is a cross belt and loose and the tight pulleys, that system is used, and in case of shaping, it is the Whitworth quick return mechanism which is used. Well, let us see the turning operation. Here the workpiece is shown here in the schematic diagram, it is a pictorial view, and I said earlier also we have discussed that this is the FF, which is the friction force. Friction force is parallel to the workpiece axis and it is normally given in the direction of the feed. So, the direction of the feed is shown here, this is the feed direction, and along that the FF, which is the friction, which is the feed force, this is located. Fr is the radial force is perpendicular to the axis of the workpiece, and Fr and Ff both are located at the horizontal surface. Their resultant will be the Ft, this we have already discussed. So, therefore, the Ft, this is becoming root over Fr square plus Ff square. Fr once again is the radial force and Ff is the feed force. Now, if you draw the parallelepiped like this, so vertically located is the cutting force Fc and the resultant force, which is root over Fc square plus Ft square, which will be located from the back point, that is the tool point, to the front point of the parallelepiped. So, the resultant force is becoming root over F c square plus Ft square. Ft is here. So, these are the 4 components basically, that is Fr, Ft, Ff and the Fc, and main 2 components are the Fc and the Ft. So, therefore, I also said earlier that when cutting forces are measured, there normally is the Fc and the Ft, these 2 components are measured. Okay. Now, if you see the view like this as it is shown here, so this is the tool and it started machining. So, this much depth of cut has been machined, all right, and let us say the tool position at a certain time is here, and after one revolution of the tool, one revolution of the workpiece, and the revolution of the workpiece is n, which is given in RPM, that is the revolution per minute. After one revolution of the workpiece, the tool has moved from one here to here. So, this distance, the movement of the tool or advancement of the tool per revolution of the workpiece is given as a feed. So, therefore, the feed unit is millimeter per revolution. How much millimeter the tool has moved with one revolution of the workpiece. This is the width of cut, this is the width of cut. Okay. I think somewhere it is written also. So, width of cut, and if you now draw these 2 lines, extend these 2 lines, or if you take a section like this, let us say AA section, that AA section will look like this. Okay. Here this is the distance between these 2 lines will be given as the T1, which is the uncut thickness, all right. And if you see the AA section, this is how you will look the workpiece and this is the tool. So, therefore, this is the rake face, because over the rake face the chip moves, and this angle is the rake angle, which defines the inclination of the rake face, and this is the flank face, which makes an angle with the already machined work surface as the flank angle. So, this is the rake angle and this is the flank angle, which we have discussed also earlier. Now, in the force components, the Fr can be found out from Ft and the sine of the gamma s. Gamma s is the side cutting edge angle. I am once again repeating this, we have said that. So, gamma s is here. Okay. So, if you see this, if you see from this figure particularly, you can find out the Fr is equal to Ft and the sine of this angle, that is the side cutting edge angle. Similarly, the Ff, that is the feed force component, this will be equal to thrust force into the cos of the gamma s. Gamma s again is the side cutting edge angle. And in the geometric parameters, width of cut will be equal to the d divided by cos of gamma s, that you can find out from this small triangle. Let us say this small triangle, you can find out that the w, which is this, is equal to d, which is this, divided by cos of the side cutting edge angle. And from a very small triangle like this here, this triangle will define the value of the T1. T1 is from this point to this point. This is equal to F is this is the movement of the tool per revolution of the workpiece into cos of the side cutting edge angle. So, these are the geometrical parameters. W into T1, as you understand, is equal to D into F, because the cos gamma is getting cancelled. So, W and the T1 is equal to F and the D. That is what we get from the geometrical relationships. Now, the power consumption, that is the during the machining, during the turning in this case, the power consumed can be given as Fc into Vc. Fc is the cutting force component, which is here, into the Vc. Vc is the pi d and the n, this is the cutting velocity, all right, plus Ff into Vf. Ff is the feed force is here, into the Vf, which is the feed velocity. This is the feed and the velocity is given as a feed velocity, all right. Now, normally what happens, the Ff is much less than the Vf is much less than the Vc. Vf, as we said, that Vf is the feed velocity. Okay, let us say feed velocity. Now, the feed velocity is much less than the cutting velocity. So, therefore, in here the Ff into Vf can be ignored and the power can be written approximately as a product of Fc and the Vc, that is the cutting force and the cutting speed. Power can also be given as the Uc, this is the specific energy, and the material removal rate. Now, the specific energy in case of turning is the energy which is spent to remove unit volume of material, and this is given in joules per millimeter cube as it is shown here. The specific energy is the energy required to remove a unit volume of material, which is joules per millimeter cube. Okay. So, therefore, finally, we are saying that the P power can be written as either Fc into Vc or Uc into MRR. These are the same thing. Uc into MRR is equal to Fc into Vc. Okay. Now, the Uc, that is the specific energy, there is an empirical formula. Empirical formula is the formula that is obtained by experimental analysis or the experimental results. So, the Uc can be expressed as U0 T1 to the power minus 0.4. T1 is the uncut thickness and U0 is the specific energy to remove 1 millimeter of the T1. So, sometimes it is called the specific energy constant. Okay. This is also called the specific energy constant or coefficient. Okay. because it is the energy that is spent to remove 1 millimeter of the T1. Okay. Now, the MRR, material removal rate, is normally given as a product of area and the volume. Okay. So, area here in case of the turning, it is the feed into the depth of cut, and the area and the velocity is the pi d n, and we are dividing by 60 to make it as a millimeter cube per second. So, material removal rate is given in the unit of millimeter cube per second, and UC is the joules per millimeter cube. So, number of revolutions per pass, suppose we have a cylinder, we have a part which is being turned. Let us say this is the central line, and here we have the length of L, okay, and this is being turned with RPM of n with a feed of F, all right. So, then the number of revolutions per pass you understand that in one go some part of the material is removed, okay. So, that is called one pass. So, there may be several passes for getting the final depth of cut removed. So, number of revolution per pass will be dependent on the L and the F, that is the feed that we are using. So, it will be given by L divided by F. Therefore, the time that is taken in one pass will be given by L by F, number of revolutions, into the total number of revolutions that you are using, n. Okay. Therefore, the total time that is taken for machining this, depending on the number of passes, that will be equal to L upon F by n, which is the time taken per each pass into the number of passes. Number of passes can be 1, number of passes can be several, it can be 2, 3, depending on how the material is being removed, what kind of material and what kind of tool and so on. So, n small n is the number of passes, L as we said the cylinder length, spindle speed is n, and the feed in millimeter per revolution is F. Now, let us see what happens in case of shaping and planing. Now, in shaping and planing, as you understand, the tool used is almost the similar to the tool that is used in the case of the turning. So, here is the diagram which is shown in case of shaping or planing. Only difference is, as I said, that in shaping the tool moves, tool reciprocates, and in case of planing the workpiece reciprocates, otherwise there is no difference as it is. Now, here the forces are the following, that here the Fc will be acting along the Vc, Fn will be acting perpendicular to the machined surface, and Ff will be acting parallel to the feed direction, along the feed direction. So, Fn and Ff, it will actually give you the Ft. So, Ff can be therefore found out by multiplying Ft and the cos of gamma s. Gamma s in this case is this angle, all right, and it is called the primary principal cutting edge angle. In case of turning, it was the side cutting edge angle. In case of shaping, it is called the shaping or planing, it is called the primary principal cutting edge angle, and therefore, the normal Fn can be found out by Ft and the sin gamma s, all right. And the geometrical parameters, like in the case of the turning, the width of cut which is here, this is found out by d divided by cos into the primary principal cutting edge angle, and the T1 which is the same way we are making it as we have done it in case of turning. That means, we are taking a section xx, and this is the sectional view xx. So, therefore, this is the T1, and we have the tool and the workpiece with the rake angle and the flank angle. This is remaining the same as in case of the turning operation, as you understand. Now, the power that is utilized or that is consumed during the shaping or planing, this is given the same way again, UC into MRR. MRR, material removal rate, is area into velocity. So, area here is F into d, that is the feed and the depth of cut, and the velocity it is taken as the average velocity of cutting here Vc. This is the direction of the Vc. Okay. So, we have the geometrical parameters, we have the forces and the power consumption here for the shaping or planing. Now, let us see that how much time it takes for shaping a particular length and the width of a part. Let us say we have a block, all right, and this block has to be either shaped or it can be produced by planing. So, in here the length is L, capital L, the width is B, there is a breadth, and here in case of shaping, unlike in case of turning, the tool moves very rapidly up to the point where it gets in contact with the workpiece. Then the speed of the tool slows down, and then from here it again goes with that same speed as it was approaching initially, because when it is approaching it is not cutting the material. So, you understand that the speed could be higher. So, this is called the approach length. This is small l from here to here. The tool tool is located here, it is approaching to this point, this is called the approach length. This length is the same in here, and this length is the length in through which the tool is removing material. Okay. Cutting process takes place along the length L. Now, here it is written approach length is small l, V is the average velocity of cutting, F is the feet per stroke. Mind it, as I said that it will go and come back, tool will go and come back. For example, it is in case of shaping. So, it goes forward and come back backward at a higher speed. So, this is one stroke, tool going forward and coming back. That time during that stroke, that is going forward and coming back, the workpiece is getting a feed perpendicular to the direction of the tool movement. So, this is called the feed per stroke therefore, and R, let us say this is quick return ratio. Depending on how fast you want the tool to come back, in case of shaping I am talking about. So, then that quick return ratio will depend, let us say this is given by small r. Therefore, time taken for the forward motion will be this L it is covering plus 2 of this approach length it is covering divided by velocity, average velocity of cutting. This will be the time for forward motion, and for the backward motion it will be Tf this time divided by the quick return ratio, okay, because how fast you want the tool to come back, depending on that value can be determined. So, therefore, the total time taken per stroke will be Tf, which is the time for forward motion, plus time for backward motion Tb, and this will give you L plus 2L divided by V into 1 plus 1 by R, if you take these two, sum this up to 2 of these values. Total number of strokes to cover the B, see this is one pass and then the feed is given, then there is another pass and so on. So, total time taken to cover the B is equal to, if you the total number of strokes will be B by F depending on the feed. Okay. So, therefore, the total time per pass will be equal to B into L plus 2L by V into F into 1 plus 1 by R. This is the total time for removing the entire. So, actually this is, I would like to remove that, please correct it, this is not the total time per pass, this is the total time required, because total time per pass we have already discussed earlier. So, the total time will be, to cover the surface B by F you need these many strokes into the BL plus 2L by V into 1 plus 1 by R. So, this is the final expression for the total time that is taken for making the entire, I mean removing the material with the desired depth of cut, okay, of this kind of a part with L and the B size. Now, in case of drilling it is different, because first of all in case of drilling the forces are different, that is both the rotation and the feed is given to the tool, that is that is to the drill, and here is a diagram shown. As you can see that suppose drill initially was at this point, and with one movement of the drill it has gone from penetrated from this point to this point. So, therefore, the distance between these 2 points will be feet by 2, half of the feet, because there are 2 teeth. Okay. In comparison to tools used in turning, shaping or planing, here we have the 2 teeth. Okay. So, therefore, this f will be distributed amongst these 2, and this distance will be f by 2. And if you take the cross section here, suppose let us say this is AA, and the AA will be seen like this. If you see here, this is exactly the same as what we have done in case of turning or shaping or milling. Okay. This is the rake face of the tool, this is the flank face of the tool, and therefore, it is the rake angle and this is the flank angle. This is for one tooth. So, therefore, there will be 2 teeth for the drill. Okay. Now, here the geometrical parameters will be the T1, this will be equal to f by 2 into sine of beta. This is the angle beta. All right. So, there is a cutting, like in the case of the turning we had the cutting angle, here we have the point angle. Point angle is the 2 of the beta. Okay. Point angle, this is twice beta. So, the beta is half of this point angle, and here the T1 is equal to f by 2 into sine beta. This you can find out in a similar way as we found out earlier. From this small triangle you can find out the value of the T1. Okay. Now, the width W, width of cut is here. Okay. This is the width, and this width you can find out as d by 2 divided by sine of beta, this angle. This also you can find out from a triangle from here, if you do that, sorry, this will be a triangle, let us say. So, from this triangle you can actually find out the value of the W. This is related to the diameter of the drill. Here is the diameter of the drill or the diameter of the hole that it is being drilled. By the way, when we are drilling a hole, normally the hole diameter becomes little more than the drill diameter, because the drill vibrates. Okay. So, similarly, we cannot say really that this is the same, it will be slightly different, but let us assume that d is here is the diameter of the hole. Okay. So, therefore, this will be d by 2 divided by sine beta. Beta, once again, this is half of the point angle. Now, the thrust force and the torque and the power can be measured like this, that is the thrust force is 2 into Ft. Ft goes in here. I will remove this because otherwise it will not be visible. Now, the Ft is, these are the 2 teeth. Now, Ft will be from here towards the, it will be perpendicular to this and towards the center, towards the axis. Fc will be like this, it is visible in other view, and here therefore, it will be as cross and the dot. All right. So, here you can see that this is Fc, which will be withstood by the torque given to the tool. So, this is resistance to the torque given. So, therefore, it is in the another direction, as you can see. So, this is the Fc and this is the Ft direction. These values can be found out like this, that the Ft thrust force sine of beta again, and the torque is Fc into d by 2. It is assumed that this is d by 2. All right. Now, power is taken in a similar fashion as in case of turning and the shaping, which is uc into MRR, or it is u0 T1 to the power minus 0.4, which is an empirical formula. Rest of the things we will discuss in the next lecture. Thank you for your attention.